Okay, so here are the three components of this, the major verification task that we'll be doing in this. By the way, have you two decided who you'll be working with?
I asked Chandradeep and he said yes, but I'm not sure. Like, I'll have to ask him again.
Now he's here. Is he here?
Yes, it's fine. You'll work with Siddhant. So I told him like let him announce the project first and then we will talk. But now that you have, it's fine.
I didn't understand your question.
No, Siddhant asked me. I told them let him announce the project first. But now that you have announced, I think
Okay. So you guys can later on after discussing as well. Okay, so the first component of this project, involves in just using EVA itself to verify certain design agnostic properties by running EVA on the emulator code. That is, in order to show that the code is free of the following kinds of runtime errors. Okay, so I've listed 4 of them. I don't know if EVA supports anything else that is of interest, even that might be of interest to add.
Yeah, I think these are the main things. I think there's also division by 0 and such arithmetic exceptions.
I think, yeah, that I will include. Okay, that's overflow, underflow, division by 0. Yes, I meant to include that. Yeah, and then, when you do that, it will generate a list of potential violations of those errors and their locations. Okay. And that is the first part of the task. Of course, EVA will, use a combination of whatever domains that it supports. Okay. So you don't have any control. This experiment, the first part of your subtask, the first subtask, not involved in controlling those domains, etc. So it throws all those domains and then gives violations. I don't know if there is anything more interesting that can be done with EVA, because it does not even give any information. If it has found real violations, does it? It only shows violations. It does not show any distinction between real violations and potential violations. Does it, Digant?
No, it does not. It will only give you violations, and the only thing you have is the range of values that it has derived. So you just have a violation based on the abstract domain. It will only give you the violation and the abstract domain, nothing else.
Yeah, but in that case, you can inspect the abstract domain. Okay, So you can inspect the actual inductive invariant that it produces, okay, at that point, and that by sometimes by inspection itself, you can but you don't know if that is no, you cannot do that. Yeah. Okay. I'll take it back because correct, because they're over approximation of the invariants. Yeah, so you cannot make a yes. Okay, no. So yeah, it does not do any further check. Okay, so that's the first part of it. The second task is to exactly, usually what do they do when typically when they use for software verification people, they will have to pour through all the violations or warnings that an EVA-like tool, a static analysis tool describes. And based on their, the software engineer's understanding of the code, they'll have to determine whether it is a real error or not. Okay? Therefore, that requires significant effort. And therefore, this part of the motivation for this project is to use CBMC to make the job of checking whether those warnings declared by EVA is or they are real or not. And how do you do that? Is your second task. You have to come up with a method to perform this task. Okay? For each of these kinds of errors that is that it reports, you will have to do a thing. How do you do it? I mean, you'll have to make an assertion at whatever location that it does, and then prove using CBMC that assertion is not violated, okay, or it is violated, or it is not violated. Okay. Usually in this, okay, that is okay. When I say a methodology, I mean you need to. I'm not saying I don't intend that you'll have to come up with some automatic tool or anything. Just a set of systematic methods so that you can use that for then discharge all the warnings that you get out of EVA. Now,
I have a question.
Yeah.
So are we supposed to detect all possible, or rather, are we supposed to check all the possible errors or only a subset of them?
Oh, I think because this is a team project, I mean, I want to, okay, let's, and I want you to check everything, okay? I'll tell you why this is still maybe doable, okay? Not just because you have two people on your team, okay? So you can share your burden, but there is enough tasks here for you to do. But I think especially referring to the second one, yes, a simple answer to the question is, at first cut, I want you guys to discharge all of them, okay? You may get hundreds of them, okay? But CBMC already provides some automatic thing, okay? So it actually, for each of these kinds of things, not sure about uninitialized variables, okay? Except for uninitialized variables, CBMC, when you use with an appropriate, already gives you assertions, okay? So you don't have to literally, if say you have 100 violations that EVA reports, and technically what you have to do is to make an assertion and then insert that at the right point at those locations. CBMC tool automatically generates those assertions as well, okay? So your task of at least making those assertions and inserting them annotating at that appropriate location is already automatically done by CBMC. And you could, and if you figure out a way to do it, which is, CBMC, you will have to do by unwinding, okay? So that is where you will have to use your smarts, at least the clerical, some part of the clerical part of the work is automatically done for CBMC. This is a suggestion that I'm saying. What remains for you to be done is, then you can use CBMC to verify one assertion at a time, okay? I mean, it starts checking one at a time to see if it is given some unwinding depth, etc. It is then that you will have to use some smarts, okay? And try to do as many of them, okay? So what I want you to think about what it, so let's see, who are the people who joined? Okay. Yeah, for those who joined late, I'm just going through the verification. This is the major part. The other ones will be more like assignments, so you don't have to worry about this. This is the significant thing. So that depends on whether where those violations are located, okay? If they are kind of inside the loop, if they are dependent, if those violations are somehow dependent on the behavior of the loops in your code, then you may not be able to discharge all of them. Maybe some of them, if they are real errors, you will be able to check. But if they're not real errors, so what do you do with CBMC when you want to check an assertion? Siddhant, what is the first way of you would do?
I would just put the assertion and just run CBMC.
Yeah, you run CBMC, but I want to get a little bit more, okay? You can run CBMC, but if there are loops, you will have to control those loops. So
yes.
You will be able to do. Otherwise, it will unwind, for all the loops in your code for all until it keeps on. I mean, until the unwinding is done. Okay. So those, and so you'll have to be a little bit careful. Okay. You will have to review the code, and there'll be lots of loops. So primarily, you will have to have a way of handling those loops. So you could, depending upon where the loops are located, what kind of loops, you will have to kind of review the code a little bit and understand what those loops are doing to some extent. And then you have to unwind them, all the loops up to a certain depth. Maybe you'll get lucky, and some of them you get violations. Okay, then you could separate them. Okay, so even for some limited unwinding, if you do get some violations, then you at least have checked they are real errors. Okay, but if the warnings are not real errors, okay, but they're actually they're spurious errors, then you won't be able to, you may not be able to do, you'll be able to certify it, the fact that it is a spurious check, only when you have. How will you certify? Anli? How can you, with CBMC, you had, see, with CBMC, so I'll split the question into two parts, Anli, if you're there, okay, if you want. If you do not have any loops, if your program is loop free, then there's no question of unwind. Correct, Amli?
Right, sir.
Yeah, then, yeah, I mean, this issue is not there. Okay. Now, if you, because, there's no unwinding. So, but if with a loop, when can you be sure that your assertions say either which is inside the loop or outside the loop? Okay.
Mhm.
Suppose your assertion is outside the loop. Okay. That is after exit of the loop. So if you want to be sure that your assertion is that there is a complete check, what do you have to do in order to get a full certification?
So put a statement right after that to check if
Yeah,
it's
that is right. You put the statement after that, I understand. But you may end up having to unwind the loop to its full unwinding. Okay, because if you unwind, if the loop is expected to go on for, in the worst case, for 10 iterations, and then if you put only for 4, then then you may not have verified it for all possible ways that you'll only would have verified it for up to 4 iterations. Correct? Huh?
so.
That's what I'm referring to. So as long as one way is to unwind all the loops in your program, or depending upon where the location of your assertion is, so you'll have to use certain cleverness in here in order to see how many loops you have to unwind to what unwinding depth. So this is the real problem when you use any formal verification tool in practice. If it's a toy problem with 1 or 2 loops, then maybe you could unwind all of them to its worst case unwinding depth. But if you have a code like, in this case, 1,000 lines of code, then there'll be a problem. But anyway, I don't want to, I'll take too long. Okay. So there is, I can't address this. I want you to think about this. Okay. I mean, after reviewing this task, and we will get to discuss later on, because otherwise I'll be taking all the time and won't be giving any time to Diganta to review the code. Okay. Which is quite important. So that is what I mean by methodology, because you will have to figure out a way that you can actually deal with loops. And I think you have learned enough so far in the course, okay, in order to figure out a complete methodology as to what you can do. I want you to think about that and how you can come up with a practical way of implementing, so that you will discharge as many of these potential violations reported ever. Now, here I am assuming that you'll be, my expectations for you to do all of them. Let's see how it goes, because we have not done this exercise. This is the first time we are doing it. So you try, and then we'll see how many. So okay, then that is the first B, the second task. C is a methodology for formally verifying correctness of the emulator. See, the first part is only verifying certain, the design agnostic, as I call them. These are errors that should never occur in any program, whether it is a correct program or not. So, whereas in C, you are trying to verify that some properties, I call them correctness properties, because they address the behavior, that some aspect of the behavior of the emulator. Okay. So, for example, you could, the emulator is supposed to execute individual instructions. So, for some subset of instructions that we will give you, one task is to check if your program is, each instruction, if you just execute one instruction on arbitrary inputs, okay, if it behaves correctly or not. Of course, what you need to check depends on what kind of instruction it is, if it is an arithmetic instruction, load, store, or control, etc. Okay, so first thing is I want you to check if it was some one arithmetic instruction, what it is that you would verify. How would you verify that? That will mean that you will have to figure out what is the assertion that I'll have to make in CBMC to do that. Say for one arithmetic instruction, pick an instruction in the arithmetic class, pick an instruction in the load class, the store class, and control the control, I can jump and branch and so on. And then figure out how you do. After that, then you could extend your basic scheme to more of those instructions. Okay, so here we will not expect you to do for the entire instruction set of 8086 because that would be quite a task. So maybe one instruction in or maybe a couple of instructions in each of these classes. Okay, by class I mean in the instruction class. Okay? For which you need to kind of review your ISA, the 8086 ISA. By ISA I mean instruction set architecture, which describes what each instruction is how each instruction is supposed to behave. Okay? And then use the scheme that you have come up with to verify a given set that we will specify individual instruction. But you start thinking about it, and you can actually pick one arithmetic instruction of your choice and then in testing your methodology. Then the second part of this third subtask is use your methodology to verify given. Develop a methodology to verify. This is B, CB, task big C, B I'm talking about. Okay, so here is develop a methodology to verify if a given arbitrary piece of code, here a code is some machine instruction, is correct with respect, after all, it's a program. So you can specify the expected behavior by giving it a pre and a post condition, which you've already seen in class, how you could do for a program. Okay, so assuming that is a given specification for that program.
But for any arbitrary program, won't that be like true and true?
Yeah. Let me complete my sentence, and after that, I'll get to you. So, for any particular program, is what. I said, okay. I know what you're picking on. Okay, yeah. No, I shouldn't be saying arbitrary. By arbitrary, I mean any given. Okay, any given. Okay, remove this term arbitrary. Okay, but I mean the reason I said arbitrary is because the methodology. Of course, you'll be able to use your methodology for a particular piece of code. Okay. But your methodology could be applicable for any code. Okay? You see the distinction? After all, core logic, we've been talking about verification methods and so on. They are applicable to any program, but of course you'll be the scheme, the algorithm, or the methodology is applicable to any program. But when you apply it, of course, you will be applying it to specific programs. Okay, but when you set it up, okay, suppose, I want you to think of how you would go about verifying that if you have some code, okay, what does it mean to say that code will produce that result? Okay, I'll give you a hint. Okay, so you will have to use you have to run the emulator on that with that particular piece of program probably loaded at some entry point location in the memory, and then you will run the program. if you run the program, then this is where, of course, you will use the emulator to run the program. Of course, you'll have to formulate your assertion such that when you run the program, you'll be able to, you should run it on arbitrary inputs. The program instructions might be specific, okay? That is the thing, but the inputs that they will take could be arbitrary, or, should be not arbitrary, but for any input that satisfies the precondition. And then when you run the emulator, and say the emulator terminates, then if you read the output, here I'm using quote unquote output, that it should satisfy the post condition. So when I say a methodology, what it means is that you will have to kind of develop a scheme as to what assertion that in CVMC you will have to check in order to, which when verified will certify that particular program will meet the pre and post. And that's what you have to think about. Now that scheme will be generic, okay? That is applicable to any program. It's not a complete algorithm, anything. It's just a set of steps that you will have to do, and then how you make the assertion. And then that is the first part of it. The second part is then you will use the methodology to verify a set of programs provided to you by us. Okay. And once again here, the program, the complexity of the program will mean whether it is a straight line program or a program which has loops in them. So we will make some small, simple programs. Okay.
Sorry, I have a question about this.
Yes.
So why exactly do we need to do this step? Because isn't it enough to just verify the emulator? Why do we need to test some external code against the emulator? If I
This is one way to verify an emulator. Okay. Okay. Why don't you think about it? Okay. I'm claiming if I can do this, even this is not a complete verification of emulator. You see, verifications of these kinds of complex systems, like a compiler, emulator, operating systems, okay? Those things are very complex. How do you verify a compiler? So you think about that, okay? I don't want to, your question, and I don't want to, I'm already getting late, so we'll have to do. So I'll answer the simple question. So when you said, why not verify the emulator itself? But what is the correctness condition for an emulator? See, for a simple factorial program of the kind, that is the level at which we have been looking at our examples. You know what the thing is. Now you can specify as a post condition and then given some input which is not negative, maybe the factorial program is only expected to work for non-negative numbers, then your output is some factorial. Okay, so you will actually check, you will define factorial in some other way, in a direct way, in arithmetic or mathematical fashion, and then you can check. Okay. Or you can do that. But what is your correctness condition for an emulator? Who asked that question, I'm asking. I'm answering your question by another question.
Yeah, I understand. But so my point was, then this is just testing, right? This is not really verification.
No. See, there is a difference here. Okay, and it's good that you asked that question. We are still. This is now, if you're able to prove that for all programs, if what I'm doing, yes, it is testing in some respect, okay? It is, okay, here's one. So it is definitely proving that the output that it produces, the emulator, on that program, for all possible inputs, for all possible behavior of that program, it is working correctly, correct?
Yeah.
So it is not like testing alone. It is a little bit more than testing. So it is checking that. So see, the first part is checking each individual instructions if the emulator emulates its execution correctly. Okay. Whereas here I'm checking for any sequence of instructions that I'm doing it correctly or not. Okay.
So if every individual instruction works according to the original specs, then won't the sequence be guaranteed?
Yeah, I think these are all very good questions. Okay, I claim that it is not. Okay, now for example, if in your compiler, if you know what each instruction compiles to, is it good enough? Because I mean, these compilers, they use a lot of conditions that individual instructions, it depends on the context and so on. Okay, in the way that it works, you will get a certain level of assurance by verifying that, but you will have to also verify sequences of instructions in different combinations and so on. Okay, so you will have to do that. So really a compiler verification in its totality is such for all programs. If I run the compiler and I get an equivalent, the output of a compiler, then those two programs, say it's a C compiler, the C program and your output object program that you get should behave equivalently on all inputs. And this condition should hold good for all programs. That's your ultimate objective. Okay, but in order to do this, you will have to reduce that. Okay? That's the ultimate compiler verification holy grail. Okay, because you will have to say that the output for whatever program, the output for all programs that the compiler takes as input, the output program should be equivalent to the input program. Okay, by equivalence I mean that those two programs should behave the same way on all inputs, and this condition should be true for all possible programs for all possible C programs. Okay, that is your ultimate condition. How will you verify that? So by just checking individual instructions is not clear because compiler uses so many tricks in the bag of tricks. Okay, that are are determined by some sequence of instructions and so on. So you will have to move. I mean, there's a question. So let me see. What is Sudakshina? Can you elaborate? Certified compilers. Yeah, maybe you want to add something. Yeah.
No, actually, I'm telling that for all the inputs, if we have to ensure that it has to be like the output has to be equivalent with the input, then compiler should come up with a certificate that it will guarantee that the input will be correctly transformed to the output program.
Yeah, that's correct. And this certification on compilers, what they do is they have a whole bunch of benchmarks. No? So they don't check only individual instructions. Certified compilers, even when they don't use formal verification, they usually say that they have this whole set of benchmarks that they run. that they certify that that the code it produces is equivalent. Okay, so that's a whole, yeah. So that's the point I'm making. So how do you provide that certification via formal verification, just like the certified compilers by certification? There are benchmarks. Here the hope is that you will reduce the problem of certifying on all for all programs by actually reducing it to either some typical set of programs or some individual instructions or some sequence of instructions. Okay, so there is a big theorem there to reduce that holy grail certification criteria that I came up with, that it should compile all programs correctly. How you would express that in terms as checking some finite set of assertions. So all I'm claiming is, you think more about it, if you just verify individual instructions, that is not good enough. Okay, is the point that I'm making. And this is extending that to some programs, okay? Some programs, and so that's one way of getting better assurance. And I want you to. This is So that's the point I want to make. So I want you to review this and come up with these questions, either questions about the specific tasks that I want you to that I have asked you to execute as part of the project, or your general questions about the question that was raised, what it means to certify emulators. Okay, is a general thing that we can have a separate discussion on. After each of us, after we all have an opportunity to think about it, and there, as part of it, I can elaborate more on why I claim that it is not enough to verify one instruction at a time. Okay. Yeah. Okay. So, any other general questions about this task? I mean, we will revisit it. Okay, in every class from now on about this. Can I move on to Diganta, or is there any pressing question? Okay, if not, Diganta, I will stop sharing.
Yeah, so I'll just start sharing. Just make me the host or the co-host.
Will this be the only project, or will there be more?
I think you can assume this is the only project, okay? Because I said that I will have an assignment on one other. There'll be one other assignment, and there'll be a small quiz. Okay, these two things will be there. I mean, you can call that as an assignment as part of the project. Okay?
So I mean, will there be alternative projects, or will this be the only
no,
one?
you can see. That's where I repeat again. Okay, so the other part, even if you call it as a project, it will be a small task. Okay, so but that will be an individual thing. Yeah, so that's why you can consider it as an assignment, or which is separately or a task, an individual task that will be part of the project. Yeah, but as okay, if that is still confusing, let me call that as an assignment. Okay, but some part of the weightage from the project will be given to that. Okay, that's all I'm saying. Does that answer your question?
No, I was asking if like all 6 of us are going to work on 8086, or
no. I told you that this part will be 2 of you pairing to work on this. Okay.
Yes, but like, will all 3 pairs do the same project, or will they be do different?
They'll be doing the same thing.
Thank you.
Yes. Unless, I mean, see, we have, okay, if you, that I don't know if I'll be entertaining or not. If you come up with some good reason that I don't want to do this, and you want to come up with some other thing equally significant exercise, a case study in verification involving these two tools, we are willing to consider. Yeah. But that has to be done very quickly. I mean, was your question motivated because of that reason?
I was just wondering.
Huh?
I was just wondering.
No. I mean, yeah, everyone will be doing the same thing. And after all, if you team up in pairs, there's only going to be 3 teams here. Yeah.
Okay, so I guess I'll demo some of these 8086 emulated and the code as well. So let me share screen. Right. So, okay. So I think the first step that I'll do is sort of go over installing this.
Increase the font size.
I will do that. Yes. I'll go over the simple things like okay, let me just. Okay, that's it here. Yeah, I'll go over simple things like installation, building it, the dependencies you'll need, and basic usage, like how do you use it, how do you exit out of it, and such things. So yeah, so firstly, this project is this emulator is called 8086 Tiny. It is fairly old in the sense that it is something like, okay, it's from 2010s. So in that sense, it's old. So if you were to clone the repo, and I suggest that you clone my fork of it because that contains some extra scripts and some changes in the README and so on. But
Diganta, in terms of time, if we can all agree that 6:15 is when you close. Okay.
Yeah, sure. So 6:15 means half an hour, a little less.
Half an hour. Yeah, we can continue this. Okay. Yeah.
Yeah. Sure. Yes, of course. Yeah. So I'll maybe just go briefly over the code, but I want to like at least show you something that you can try with the emulator on your own and see if it's even working on your end.
That would be good. Yes.
Yeah. So first things first, you'll have to clone the repo, which I've already done, and I suggest that you clone my version of it. So the folder here that you're looking at is this 8086 Tiny folder over here. So you clone my fork of it because that has got some extra README and scripts and such things, as I was saying. And if I do any changes to the C code, I've not done that yet, but if I do that, I'll put it there, but I don't think it'll be necessary. Yeah, so I'll just do make clean quickly, so if you clone the repo, this is what you'll see. Okay, so there is your original your C code is there, your README is there, makefile is there, and then there is a few other things. So this is license and README and all of that is fine. There is a few other things, which is 3 scripts. So you see there's the script run me, and then there is 2 other scripts which I have written by modifying run me. I think I'll remove this tags file. Okay. There is also this tags file is something that I use personally, so it's fine. There is also this thing called the BIOS. If you look at over here, so this is the binary BIOS that the emulator is using, and I'll explain what that is. If not like in details, if I don't explain it today, then I might explain sometime later. But if you know, every PC has sort of a BIOS ever since like PCXT. So this is whatever that BIOS is. And then the emulator boots from floppy disks. So they have given us a default floppy disk to boot from. Okay, so these are the few things that we have over here. All right, so before you try building it, you need SDL, and that is SDL1, not SDL2. So so SDL1 is technically speaking deprecated, but it's not like SDL2 is not backwards compatible with it. Since this one uses SDL1, you will have to install that. I have written in the README where what you need to do to get SDL1 installed on various systems. So if you read this, you'll see what. So I've talked about OS X, Ubuntu, and Arch, and the packages you need to install to get SDL1 over there. Okay, so the good way to check. Okay, so maybe I'll write this in the README as well. But a good way to check what your SDL1 installation is, or whether it's correct or not, is to just run this particular command. If your SDL1 is installed, then this command should give you something. It should not come up as, yeah, so it should give you some compiler flags that you need to compile with SDL1, and the makefile uses this command to get these flags. So once you have SDL1 installed, you can just check whether the installation is fine by running this SDL config. Okay, so once you've done that, then building things is very easy. So you can, yeah, so one thing is this SDL1 is not strictly necessary. This SDL library is only used for the graphics and sound capabilities of the emulator, which is optional for our purposes. So if you don't want to, or if you at all cannot install SDL, then you can avoid that by building a different version, which I'll show. But say, suppose you have installed SDL, then you just build it by using, just by running make. Yeah. So it'll run and build your binary for you, which is 806 tiny. And then you can just run it by running the run me script. I'll do that in a second, but before I do that, if you don't have graphics, in the sense that if you can't install SDL1, then what you need to do is just run make with this no graphics target. Okay. So then it will build a version which does not use SDL, but also does not have any support for graphics and sound. So it will only give you just plain text terminal and such things. So you have two options. I'll say that, try and get the SDL installed and use the SDL version. But if you can't, then just go with the one that has got no graphics part of it by just doing a make no graphics, right? So if you can install SDL, just do a normal make. If you at all can't, then do make no graphics. Of course, if you want help, I'll be there to help you install SDL. Any issues, just let me know. So I'll just go back to the original thing. Yeah. So now once you've built it, a quick way to test whether it's working is just run the run me script. What this will do is it'll like boot into this floppy disk image that is included within the repo. Right? It'll use the default BIOS that included within the repo and boot into the floppy disk image that is also given within the repo. So when you do the run me, it boots into the floppy disk, and right now we are running the emulator, and it is showing whatever OS is like inside the floppy disk is supposed to show. So the floppy disk is it comes with FreeDOS, so it will give you the FreeDOS license, and it will also give you some data regarding what all other things are there in your PC. So right now there is nothing other than this particular floppy inserted into your PC, and then finally you get into the DOS prompt, and you're in this age, right? Because that's the floppy drive. So now if you're familiar with DOS, all usual DOS commands will work. So dir is your ls equivalent, and will give you whatever files you have right now. And you can, run whatever default DOS commands or FreeDOS commands there are, you can run over here from inside this floppy disk. So this is the emulator running right now. Just as a very quick demo, this emulator also comes with this particular, as a graphics and sound demo, it comes with this game installed. Apparently this really old game called Alicat. And you can also run that just to check that. If you have installed SDL, you can run this to check that graphics and sound is working. Yeah, so we don't have a joystick. Yeah. I don't know if you can get the sound, but it's somewhat loud and such. But yeah. So yeah, so the only way to exit out of this is Control Y. And even when you exit, if you go back to this DOS prompt here, but this screen remains up, and it will give you some graphical glitches. But if you focus on it and you type into the DOS prompt, you'll get your usual, you'll be able to type your usual DOS commands and such things, right? So yeah, so this is the emulator running. As you can see, it's very bare bones. It doesn't have any GUI. It depends on your host terminal.
What did you run a program now? Did you execute the program?
Yeah. So I'm running. Program? I'm running a number of things here. So I'm running the default BIOS that they're giving. On top of that, there is the FreeDOS operating system that is running right now. So that is what is giving me the terminal output over here. So this terminal output.
For all you need, if you really want to see it, the output like in this fashion, Okay.
Right. Yeah. So
let's
this time-
suppose that I mean, there is also a bare bone version, I presume, where you will treat the emulator as a C program. And then when I just want to get a dump of the memory and the
Yes.
registration.
Yeah. So I'll show you how to do that. So,
Now this is for you to get familiar with the thing if you want to run it. Okay.
right. And then, to check whether this thing is at all installed and correctly.
Okay. Fine.
Yeah, because then you can just run the run me script and it should give you a DOS prompt. You can sort of try various things in the DOS prompt and make sure that like things are working and so on. So yeah, so this is running DOS, and on top of that, I just ran this AliCat program. So one of the things in the emulator is that if you run this run a graphical program, it will give you a pop-up screen with the graphics on it, but then it never closes the screen even if the program quits. It just leaves it open. So it is, when I say this emulator is bare bones, I mean it's this bare bones, right? So it doesn't really do any extra thing that it doesn't need to do. Okay. So yeah, and in PCXT fashion, so if I remember, like I read this somewhere, that in the original PCXT, the only real way to shut down your system was to, cut the power, like press the power button. In a similar fashion, the only real way to quit out of the emulator is to kill it. So I'm going to kill it right now. And now we have quit out of the emulator. And as you can see, it is leaving our terminal in a slightly malformed state, which we can just clear and we'll get back to a correct state. Yeah. So it's very bare bones. It'll use your parent terminal, like your host terminal, to display its own terminal. And the graphics, the UI for it is very, very bare bones. There's a less bare bones version with a more sane UI called 806++, but that is also a lot more code. So, we don't need to worry about that. Okay. So this is the emulator. All right. So let's see. Let's look at this code right now. So I think it's a good point to give us somewhat slight introduction to the code. So I think I also should probably talk a little bit about very little bit about the architecture before we go into the code, just so you know a little bit about what's going on. So just do that. Yeah. So in the this is the 8086 processor, which is a 16-bit processor, which means that addition, subtraction, multiplication, all those things are 16 bits. Word size is 16 bits. You fetch 16 bits from memory at a time, and so on, right? So your registers, you have got most of your registers are 16-bit registers. So your like 16-bit register bank and so on. Okay. So the 8086 supports 20-bit addresses, right? Because it supports 20-bit addresses, there is 1 megabyte of maximum amount of RAM, and this emulator supports that exact amount. There is 1 megabyte of RAM being emulated inside this emulator, right? So this emulator basically is going to give you a 8086 as you would find it in a PCXT machine. So this is some IBM and IBM compatible brand of machines from the late 80s, I think. And it's got 16 bits. It's got 1 megabyte of RAM, and it also emulates things like the simple keyboard and some floppy disk, hard disk, and such things. But most of those things we won't really, or at least you don't immediately need to really worry about. Most of the programs and such things will give you won't involve those things. Yeah. But what you need to know is a little bit about how you address 20 bits of, like 20-bit worth of addresses using 16-bit registers, right? So if you think about it, if you have a pointer in your CPU, so if you're not aware, a register is kind of like a local variable. If you can think of it like a local variable, right? So pointer is going to be stored in a local variable. So if your local variables are only 16 bits or registers are only 16 bits, then your pointers are going to be 16 bits, right? But how do you use 16-bit pointers for a 20-bit address? So you can't do that. So the way this PCXT systems got around that, and 8086 systems in general got around that, was via this segmentation concept. So I need to tell you this because I think this is the only part of this architecture that you need to know before looking at the code, I think, at least. So the segmentation concept is basically this, that your memory, if you imagine this is your 20-bit memory, that is your 1 megabyte of 20-bit addressed memory. This is split into several blocks. Each one of these blocks are called segments, and these are 64 kilobytes long. So you've got a 64 KB block like this, and these are overlapping. So these blocks can overlap, and you've got maybe another block from here to here, and third one from here to here, and so on all the way up until the end, right? So you've got 64 KB blocks, which are potent, like which do overlap, and your address basically is given by two 16-bit numbers. So any 20-bit address is formed from two 16-bit numbers. The first one is called the segment part of the address. So this is a 16-bit number which tells you which block you want to look at. So maybe the segment points to this particular block. And then you have, usually these are separated by colon. Then you have the offset part of the address, right? So you have offset over here. This is again 16-bit. And this tells you where inside the block. So whenever I want to do any memory load, store, or write to memory, read from memory, any sort of that operation, I specify this a segment which is a 16-bit thing and an offset which is another 16-bit thing. And there are some specific registers for the segment and which are used in various contexts and so on. But we don't need to go into those details right now. But basically, you need to specify a segment and offset, and that encodes this 20-bit address, right? So you say that, okay, I am looking at the, of this whole memory that I have, I'm looking at the segment here. And from this segment, I have my particular memory that I want to look at is offset this much. So I'm going to look at this particular point of the memory, let's say, right? So this segment and such offset. So that is how we talk about this 20 bits worth of memory. So yeah, so this is the—
This thing applies only to pointer variables or any addressing, any memory addressing.
So any memory that is reading or writing from the RAM.
Like load and store, all of them
Yes,
will have to be, the address will have to be.
Yeah, this will have to be done for them. So usually the operation, what they do is there is one specific, or at least there are few specific registers which store a segment address. And then, you can use different offsets on and on. So the usual way programs operate is that they pick a block within which they'll operate for some length of time. And they set that up by setting the segment address in a particular register. And then they just, while doing the load and store, they'll only have to pass the offset address. Okay, so the idea is you set a segment and then you do multiple loads and stores from within that segment by using various offsets. And usually, you don't, unless you're doing really far off loads and writes, which might be something that you end up having to do.
Switch.
Yeah, you'll need to switch a lot, but usually you won't need to do that. You need to just set up a segment. Yeah, so I don't think there is any cost associated to switching in the original hardware. Nothing like, cache misses in modern hardware, but yeah, it will be an extra instruction at least, if that makes sense. So you would want to reduce the number of switches. Okay, so with this, I think we'll go into and look at the code. So any questions so far? I think Chandradeep, you had seen this. You have studied 8086 architecture in detail before, right?
So no, I studied 8085.
Oh, okay.
It didn't have the offset thing.
Yeah, so I think that had lower memory support. So 8086 has got, it's a little bit more complicated, and it's got 16 bits as opposed to 8 bits, I think. Yeah.
So if I understand correctly, so multiple segments can intersect, right?
Yes.
And so that means multiple values of segment and offset can point to the same thing.
Yes, they can.
Okay.
And usually that is actually, in some sense, turns out to be a good thing, because if you want to switch, say you have stored something in this part of the segment and now you want to switch segments, then you don't need to, if you want to keep this data in the new segment that you want to switch to, right? You don't have to necessarily copy. You can just switch to this segment and you have the same data in a different offset region.
Yeah.
Right? Yeah, so you can do those kinds of things as well. So yeah, you don't have a particular segment offset is not a unique look, like doesn't uniquely point to, or is not a unique identifier for a location in a memory, let's say, right? So you can have
Yeah.
different segment offset values for the same location in memory. Yeah, and then the general formula or the arithmetic in this case is, and you can derive this very easily from the number of bits involved and such, but it's basically segment times 4 plus offset gives you the actual 20-bit address. So yeah, well, like this is the most tight packed, or this is the only way you can have it if you want to use all your bits essentially. Yeah, so that's any other questions right now? Okay, so if there is no other question, then I'll go on to the code very quickly. I don't think I've got only a few minutes.
I have some questions. Okay.
Yeah.
So I guess before you do the code, okay, so normally I'd be interested in seeing, okay, I mean, I want to use the emulator to run a program. Okay.
Yeah.
How do I, okay, so the basic questions I have, some emulators, I mean, the ISA architecture, does it have two separate memories for instruction set?
Right. I should mention that. Yeah. No, it doesn't.
Okay, so which means that you will have to kind of manage, okay, I store the program from this location to this location.
Yeah, so there is a very specific location where the processor starts executing from when it boots up.
Yeah, but that is fine, okay? But you will have to manage the data. I mean, you will have to have a data layout, pre-planned, okay? When you want to execute the thing, right? Yeah.
Yes, so, you will have to do that.
Yeah, so which means that your addressees, okay, so because this is important when you want to, if you want to check properties, okay? I mean, that store, load, and so on. Okay, that is one. Okay, so it's the same thing, means that, you know, your setup, your initial setup, even to do arbitrary verification, okay, you'll have to have some, your initial state will have to be set up in a certain way, okay, so that it, meaningfully executes your program, okay, so that, otherwise you could be doing things which will overwrite your own program. Okay.
Yes. So let me actually, you know what?
Those kinds of things, let them figure out. I mean, I don't think we can address all of them. Okay.
Right.
Just at all of them today. But the fact that they are two separate memories and updates, the same memory, and therefore you have to manage, and therefore the setting up of the initial condition, which in verification term will mean, doing it differently. I mean, it has to work for all, programs with some constraints and so on. Okay. That is one thing. And is there, and it does, okay, that's one question. The number two, do you have to do some initialization, some resetting or something before you can even start the emulator, or can you start from a cold state?
Yeah, you can start from a cold state. There is no.
So
yeah.
Even when you have not initialized your memory or something.
Yeah. Specifically, like no register or memory initialization needs to be done at all. Okay?
Needs to be done, but it may crash, or it may, who knows? It may not work. Okay, I mean, it may, but the result will be unpredictable.
Right. So if I go into the code, so they do some. So let me go.
That's these are the two questions I had. And the third question is, I mean, maybe you can address that to the code. How do I execute an instruction? Then how do I observe the contents? Okay, the memory contents.
Yes. Yeah. So I'll maybe show that in the code as well.
So that is the most important thing. In order for them to do the third task that I have described, these things are important. Yeah. Okay.
Yeah. Okay, so I think I don't have any much time left at all. So maybe, sir, what I can do is I'll talk a little bit about this first issue that you raised regarding having to figure out a memory layout, and where in memory code is and where in memory data is and so on. And then maybe I can like start looking at the code from next time.
Option is, okay, no. In terms of logistics, I'm saying we can, continue the two files. I'll ask you the questions. You describe to me. Okay. No, maybe that's not fair. Okay, and we can record it and then have them listen to it. Okay, at their leisure. So 6:30 or so. No, but that's anyway. We can record that separately also. So go ahead. So plan whatever that you want to describe till 6:15.
Yeah. So very quickly, I'll just say this. So I was saying that you load a segment and then you use various subsets to access the data. The same thing goes for your program counter and your stack. So stack by stack, I mean call stack. So the CPU has got explicit support for a call stack. So it's got like call and return instructions as well. So usually what happens is that the program counter starts from this one very specific state segment, and things before this segment is usually reserved for things like interrupts and so on. So we'll not worry about that anymore. So at all, but basically your program counter starts at the beginning of this segment. I think it's 0f00 0000. If I remember correctly, this is the segment from which your program counter starts from, right? So you have got a program segment, and that is always 0f000. So what I think we can do is to make things simple. We can limit our programs to 64 KB. And then we can also limit the RAM usage to 64 KB. So then what we can do is we can have a very separate some data segment somewhere completely.
That's what I would do. That's the initial. We have to set it up, okay, and we can define that as our initial, condition, okay.
Right.
And we can write something. Yeah. So yes. So these are the kind of things, guys. When I said that you will have to figure out a methodology and so on. So based on this information, you will have to set it up. Okay, this is all relevant for task C. I think for the first one, task, this is probably not as well.
No, it's not relevant. Yeah, but in terms of setting up the memory, you don't have to do it manually because, in some sense, the emulator will already load your BIOS into this particular segment. So the BIOS has to be less than 64 KB, and it always gets loaded into this segment. So what we'll do is when we want to pass a particular program to the emulator, we'll just compile it as some BIOS.
Okay. So that's what the is. BIOS. When you load the BIOS, is it some data being loaded?
No. It's just some program that is being loaded into this.
Why do I need the BIOS?
So the BIOS has got some very low-level input-output like commands that is used to say read from the keyboard, write to the terminal.
No, if we're not interested in those kinds of programs,
right?
The BIOS. No, we can always load the BIOS. Okay.
No, that's what I'm saying. We'll replace the BIOS, and instead of loading the BIOS that they have given us, we'll replace it with our programs. Our whatever program will act like the BIOS in some sense.
Correct. Yes.
Right.
Yeah, and then the load BIOS will be like the reset condition.
Okay? Yes, exactly. So whenever you start this thing, it'll load the BIOS, and then you can. Right. So this is.
We could do that, but I'm willing to give them flexibility if they wanted to find their own programming.
Yeah, sure.
So how will we see the memory thing? Will it GDB?
No. So when you see the memory, if you want to inspect it manually, GDB is a very good option. But when you will be doing verification, you'll want to talk about the memory as an asset inside the program, right?
Yes.
Yeah. So then there you'll have to use whatever the variable is inside there, and it'll show you the variable. So
that's the important thing. You have to make a distinction of people. Okay. So you can use this emulator in emulator run mode. Okay. To just run your program with BIOS and then do fancy things. like what he showed with the graphics and so on. But our purpose is different. Okay, maybe there will be having knowledge of doing that may help us. But here you can't be using GDB in our verification. Yeah, you will have to directly write certain functions or something like that, or use that is available to read the memory and the visible part of the state, like PC and registers and so on.
How do you reference mem in a different file? Isn't this specific to this file?
Yeah. So
Oh, external. Yes. Sorry.
yeah. So why would you want to reference it in a different file though? Like,
So the assert statement will be in the code in the BIOS code, right?
no. The assert will be in this code itself. So see, the all of our tools is designed for C programs, right? So say if you're using CBMC, then you can't add an assert in assembly in the BIOS code. CBMC can't read that. So the assert will be over here. So the idea is that we'll give you some programs and some properties on the memory that should hold before and then after, let's say, right? So then you use that, so you write corresponding asserts to that with respect to this MEM variable and whatever other variable you need to.
Correct. So your pre
Inside
and
the
post,
C, yeah.
the assertions and assumptions that you'll be writing will actually use these variables. Okay, because those things will have to be in C to work either in CBMC or even in EVA. Right?
Yeah. So to sort of, I think this is kind of related to the question that you're asking. So see, to do a complete verification of this emulator, we'll have to figure out some invariant that is very deeply dependent on the specific ISA and such things, and then say that okay, with respect to the ISA, if you do this before this instruction, things are correct, and after this instruction, no matter whatever optimization is going on over here, things are still correct and so on, right? But instead of taking on that Herculean task, we're only verifying that okay, this particular program runs correctly no matter what the initial memory is, or no matter what the other parts of the memory are, right? So that is the sort of verification that we'll be doing. So then does that answer your question, or does it clarify things for you?
Yes.
Yeah, more specifically, if the current if the content of the memory pointed to by PC is this particular is a given instruction, then that will be part of your precondition. Okay, then I run the emulator. Then when it ends, my memory or whatever, depending upon what the instruction does, ought to have something, okay, which will be specified as my post condition. Yeah.
Yeah.
In it.
Yeah. That is basically the way.
Yeah, I know Diganta is answering, but not.
Oh, sorry. Yeah. I wasn't Mr. So I'm sorry. Yeah.
I know. Yeah. Whoever asked that question.
Chandradeep, I think that was you, right? Is this clear?
Yes.
Yeah, maybe the way I speak, they don't understand whether I'm asking the question.
No, I think I should.
Okay. I mean, let them think about it. Okay, so then that's also,
Yeah, so unless there is any other specific question, I won't go into too much details.
Another question. Oh, the registers, all things are there. Okay.
Yeah, everything is here. So there's registers. So the registers are here, and it also has some macros for specific named registers that are defined somewhere about here. Yeah. See, there is there are various macros for defining what flags are what bits of which registers, and similarly there are macros for defining named registers within your 8-bit register bank. There's also an 8-bit register bank that is defined down there. Similarly, there are 16-bit registers named versus index within that bank, and so on. So all of that is there in some macros over there.
Yeah, is there a kind of instruction set description for 8086.
Yeah. So there is definitely a lot of such
That
resources
should be
available.
published so
Yeah.
that they will know for each instruction what it is supposed to do. So that will be at a much higher level. Huh?
Yeah, so that will be at say assembly programming sort of a level
Yeah,
that
but
will
that's like an assembly program, but it will really not, it will describe, oh, this instruction, this is the format of the instruction, okay, there's an opcode, there is an, the operand for each instruction is some register or a memory thing, so the entire bit, okay?
right.
Then it describes what it is supposed to do, so that if you want to load a program, you can actually do it, okay? I mean,
Yeah. And then if you're say given some assembly, you can at least like read it a little bit. Yeah, but I think what
but that is one. But I think you need to know. I mean, so what? It modifies PC and then it stores the overflow bit in some register. Okay, those
Right.
descriptions will be there for each instruction. Okay, whereas here you have to read the code in order to understand it. Okay, so if you have the ISA architecture at the high level, and if you want to know what each instruction does, okay, as an improper condition, that will be useful, because otherwise
I'll send
deep into this code, which is not necessary. Yeah, in order to specify the pre and post condition of those things. Yeah,
right. Yeah, that is true. So I'll send out a PDF.
Yeah, and that will be a good starting point to understand at a high level what each instruction does. Yeah, and what things they read from and what are the things that they modify. Yeah.
Yeah, so one thing that I want to do before sending out the PDF is that you should, since this 806 ISA is fairly big, like it's a fairly big instruction set. So
Oh, that's okay.
yeah, I just
once you organize that, I've read big instruction set and architectures. I know it's a big document, but you can learn to read it. Okay, I mean, if you just organize yourself into arithmetic and things and so on, we can do that, and we can even. I mean, they need to do it anyway. How else will they do?
Yeah. But I'm just saying certain parts of it might not be necessary. Things like
that may be so. Okay.
Yeah, interrupts and so on that we won't be. Yeah, which we can decide to not go near. So just saying that you don't have to read the whole of the document that I'll share, and I'll try to mention which parts are going to be necessary. So do you think that is okay, sir?
No. I don't mind loading it, so they can do their bit also, to filter out what jobs they need. And I mean, they don't need to read those parts that are not relevant.
Yeah.
Or we can point out those sections that are relevant instead of, putting it on us to actually do the filtering and then the thing. So let them do that for themselves.
Yeah. Okay, sure. Yeah. Okay, so I'll send out a document.
Yeah, that you can do. And I think you will have to continue this in your next class. I mean, starting next class, I will devote at least, half an hour for doing it so they can get started with this, the tasks of the project. Otherwise, they'll not be able to finish in 1 month. Okay, any meaningful way. Because we need to know not only the ISA part of the thing, that is needed for task, the third task. But for the first task, they need to know a little bit of the structure. What are there any loops here? Are there, what are the places where there are potential overflows? How exactly does it emulate? Does it execute the instruction? That a rough idea needs to be had. Okay.
Yeah. Okay.
Yeah, I think we should stop here and let them run this thing with whatever information that you're given, and then get them familiarized with this thing.
Yeah. Okay, sure. So yeah, do at least clone and run, build and run this. Just run with the run me. Yeah. So since this is using your, it's going to be using your terminal, it will set up your terminal to be in some weird mode so that it can write all sorts of non-standard characters to your terminal. like control characters and such things. So that is why there is this runme script which will get your terminal into a mode where x86 is 10, you can work, and then get your terminal back into the mode where you can work. So that is why we are running it through these various scripts. Runme is the one that will run everything as default. You can also run other scripts if you want some non-default. Like if you want to run it with some specific other floppy disk that you have and hard disk that you have and so on. But yeah, we can maybe, that is not really relevant for us as well. We can maybe demo this sometime later. So yeah, that's all. Any questions? If